Hello, Devices 2. This is Professor Late, and today we are going over lab number 7, nonlinear op-amp circuits. The first part we're going to go over is the comparator. So, part number 1 says connect the comparator circuit of figure 1, which is what we'll do next. So here's the built comparator. So what we're going to do is we're going to look at the input voltage. So we're using an oscope connecting up to our input voltage. And we're going to adjust the potentiometer until we get approximately 100 millivolts, which is what we have already. Then we're going to look at our LEDs and determine which one is lit. So we could see when we're at a positive 100 millivolts, our green LED lights. So we're going to write that in table 1. For part 4, we're going to adjust the input so that we get about negative 100 millivolts. And then we're going to see which LED lights. As you can see, our red LED lights. So that completes filling out the table for the comparator. Next, we're going to do the second part, which is using an op-amp to build a half-wave rectifier. You remember half-wave rectifiers from Devices 1, where we built them and we saw that they can turn an AC input into a DC output. But the half-wave rectifier only uses half of the wave. So we're going to build the circuit and then fill out table 2. Here you can see I've built the half-wave rectifier. One adjustment I made from figure 2 is I added in this potentiometer to allow me to easily adjust the input voltage. So in the circuit, I've attached the oscope. I've made the output blue and the input is red. So what we need to do is adjust the output peak voltage to 1 volt. We do that by adjusting potentiometer. I've already done that. You can see that our output, which is our blue channel here, which is our channel A. So each box is 500 millivolts. So it being 2 boxes tall, that makes it 1 volt peak for our output. And we'll check that with our flag here. And you see our flag is telling us we are at 987 millivolts peak. So that's pretty much 1 volt. So what we're needing to do is take a look at the input sine wave, which is in red, and see what the voltage is. So our input sine wave is at 998 millivolts, so basically 1 volt. So that's what you would put into table 2 for step 9 is 1 volt. Next, for step 10, we're going to adjust the signal level to get a half-wave output with a peak value of 100 millivolts. We're going to do that by adjusting the potentiometer. So I have this scale set up so that each box is 50 millivolts. So when our blue half-wave rectified signal is 2 boxes tall, we'll know that we have 100 millivolts. So there we have, it's 2 boxes tall, and we'll verify it with our flags. So right there at peak, we're looking at 100 millivolts for our output. Okay, so what it wants is for us to measure and put into table 2 the peak input. So that's our sine wave, our red wave, which is our channel B. And you can see in channel B, it's also 100 millivolts. Okay, for you to see what's really going on with this signal, I'm going to adjust the position of it. So you can see this is on the same scale now. I've adjusted the position down 1 box. So you can see that this is a half wave rectified signal. Okay, and as I put it back into position, you'll see that it forms with our input sine wave. So what this circuit is doing, being a half wave rectifier, it's cutting off the bottom of the sine wave. So the only thing that's going to happen with the voltage, with the flow of current, is it's going to only push forward for the top half of the wave and then do nothing. It's going to push forward again. So we've turned our AC input into a DC output. And that's what we're doing with the half wave rectifier. So that concludes lab number 7, the nonlinear op-amp circuits. So you need to do a conclusion statement for this lab after you fill in the 2 tables, and make sure you put it into your lab portfolio. I hope you have a great day. This has been Professor Late for Devices 2.